Good morning. Welcome to Krishna's classroom. We have been considering the Radon-Nikodym theorem and some of the consequences of that. In this lecture, we present some consequences of this theorem, which are very interesting. Now, the background that we have is the following. X M is a measurable space. And mu is a complex measure on X. Now, these are the basic premises on which we are going to discuss this result. Now, what one observes is the following. See that, first of all, mu is a bounded measure. It's a bounded measure in the sense that mu of E, modulus of mu of E is finite. Okay. So, it's a bounded measure because it's a complex measure. Now, one other fact is that the total variation of mu defines a positive measure this we have already seen. So these are the informations that we already have, or we have already proved, and so on. Now, see that one of the results that you can prove is the following. See, lambda can be, d mu can be expressed as h times. So, in terms of the positive measure, what you call the total variation of mu, we can express d mu, that is the measure mu, or this essentially means the following. Mu of E is equal to integral over E h for every E belonging to That's the meaning of that. Where H has the following properties. That is, H is equal to, H is a complex value function such that and H of course is an L1 function. So this is one of the consequences that you have. So you have given the complex measure mu, there is a total variation measure which is a non-negative or a positive bounded measure, and in terms of this positive bounded measure you can express the given complex measure. That is the objective of this theorem. It's a very interesting result. In fact, this is compared with this. The fact that it has and this can be written as some which is, and then is such that it's equal to 1. So this is something like a polar decomposition, or if you just take a complex number, it can be given a polar decomposition. So if you take a complex number in the complex plane Z, so this is the direction, so this you consider as a vector, and you see that Z divided by mod Z is the unit vector in the direction of Z. So this is Z divided by the unit vector in the direction of Z. So Z can be written as into mod Z. Mod Z is essentially the length of this vector. It's a real number. So in terms of this, you can write it. So this is the analogous result that we can prove for these measures. Okay, so let us now write the theorem and then prove it. So I hope you understood the context of the result that we are going to prove. Let us give the statement of the theorem. Let on a measurable space, this is a precondition. That whatever condition is given, then the consequence is the following. Then there exists H such that equal to 1 for every x belonging to x, and such that this is the total variation measure. So, in terms of the total variation measure, which is a real bounded measure in this context, you can express deviation. So, this is almost like the same thing that we have done. Okay. So, Z is written as the unit vector along the direction of Z multiplied by the length of the complex number. Okay. So, this is the same sort of result. Now, this essentially means that mu of E is equal to integral over E is the total variation for every E where E is a measurable set. Let us prove this result. Now we make the remark equation 1 is called the polar representation or polar decomposition or polar decomposition of E. Let us prove this result. Oof. First of all, you observe that the total variation measure is a positive measure on V is a complex measure. So this is a positive measure on X derived from. Now the first thing that we observe is this. Mu is absolutely continuous with respect to the total variation. So we prove this. Equal to 0. Then we have where En is a partition of E, so you take E and consider a partition En of E and then compute this sum. Okay, and then you see that the supremum of all those sum you can write, and this turns out to be the measure of the total measure of or total variation measure of. That's our definition, and this equal to 0 implies where E is of course equal to a partition of E. So this implies this. Okay, what does this mean? It implies E equal to 0 because E is the union of En, and then you use the countable sum of this joint, the measures of this joint 6. Therefore, mu E equal to 0. That is so that's the proof of that. That completes the proof of that. Okay. Here, of course, En is a partition of right. Now we can apply the Radon-Nikodym theorem to the pair mu and total variation such that HD that is mu E equal to total variation. So the existence of this existence of H on X so that proves the existence. Now what we have to verify is that it satisfies the required property, namely that mod H is equal to, we'll slightly modify this function H without any change to this particular integral. That we will do. Now we prove that equal to 1. So we prove it in the following way. We prove that almost everywhere, and wherever this is not true, we will modify H. Without affecting the the representation. So that's our strategy. Okay, so first we prove. So the claim, do it in the following way. We first prove H is so this is the first thing that we prove. Then we prove the other part, namely mod H is less than or equal to 1 almost everywhere. So that together it would mean mod H equal to 1. Okay. So let the set of all x for which we'll be working on A1 actually, where R is some positive number. Let EJ partition of AR. Then we have the following. Summation over J is equal to summation over J mu Ej is essentially, by the representation theorem, the integral over Ej of H the total variation measure. Okay. Now this is less than or equal to summation over J or we have what is it? On AR mod H is less than R. So you have this inequality. Look at the definition of the total measure of a set. And it is essentially the supremum of all this. So if this is true for every partition, then it is also true for if this inequality is true for every partition Ej of AR, then it is also true for it's also true for this mod B. Okay. So you have consequently total variation measure of AR total variation measure of R. Now if we choose R less than 1, then we have and this forces mu AR, the total variation of AR equal to 0 for R less than 1. I mean, that means whenever mod x less than, okay, but this is not true, therefore consequently almost, so on the other hand, if equal to not equal to 0, or rather greater than 0, that means by our original result you have this following: 1 upon to take this is after all mu E, okay, therefore this is equal to which is less than or equal to, this is less than 1. So what does this mean? This means less than or equal to 1, almost. So earlier we have proved that h is greater than or equal to 1 almost everywhere, and mod h is less than or equal to 1 almost everywhere. Combining we have mod h equal to 1 almost. Now let us consider the set. Now you see, this means that on a set, on the complement of a set of measure 0, h could take any value because it comes inside the integral. Okay? Therefore, we shall modify it. So let B define the set for which not equal to 1. Then you know that mod h equal to 1 almost everywhere implies the measure of mu equal to measure of B, the total variation measure of B equal to 0. Okay. Now what we do is we just redefine the function. Redefine, because it may not be equal to 1, redefine h on B to be by so this is the definition. Okay. Now consider the modified h. The modified h has the property that equal to 1 and it does not affect the integral. That means this mu, what is this? Integral over E d mu. You see, this still remains modified f. By the modified h. Okay. That means you have mu of h where on over. So that completes the proof. Okay. So that is about the representation here. Now this is the so-called polar decomposition of. Now we will look at some other consequences which uses this result. Now we have the following result, which depends on the result that we have already proved. Suppose mu is a positive measure, positive M U, and lambda E is some complex measure. GD. Then what we have is this, the total variation measure, lambda measure of E is equal to integral over E mod G dV. Okay, so this is almost like putting the absolute value in the integral, right? So we will prove this result. Now there exists, see, look at lambda, consider lambda and total variation of lambda on X. Then what we have already proved is this by the previous theorem. There exists a function h with mod h equal to 1 on X such that this is just the previous theorem that we have. Okay. Now by 1 in the statement of the theorem, we have d lambda equal to G d. This is what is given. Okay. Which implies the mu. And this in turn implies, see, equal to 1. So we can write this as equal to H conjugate G d. Remember mod H equal to 1. Let's skip. Okay. This is the result that you get. So now since is greater than or equal to 0 and greater than or equal to 0, we have H conjugate G is also greater than or equal to 0. Almost everywhere with respect to U. Okay. Now set some F almost everywhere with respect to mu, and F is greater than or equal to 0. This is what you obtain. So what is F? Therefore, you have F is positive. Therefore, you take modulus on both sides. Because mod h bar is equal to 1 and this is equal to, which is equal to F. Therefore, F is equal to mod. Consequently, we have this result. What is that? T equal to mod G du or D. That is the second segment holds good. Okay, so that completes the proof of this result. We will stop here today and then take up further consequences later. Thank you very much.